We're now going to derive a mathematical expression for the speed of sound. The initial expression we're going to obtain will shed some light on why the Mach number is such a good indicator of the compressibility of a flow.
We begin by performing a control volume analysis of a weak compression wave in a reference frame moving with the wave. As the flow is steady in this reference frame, conservation of mass tells us that the mass flowing into the control volume from the left must be equal to the mass flowing out of the control volume from the right. This is because there's no flow across the top and bottom of the control volume, and if the mass flow rates aren't balanced, the total mass in the control volume would change with time, causing it to be unsteady. The mass flow rate entering the control volume from the left is given by the density of the fluid ρ times the area of the surface A times the flow velocity, which in this case is c. This is equal to the mass flow rate exiting on the right, which is evaluated in exactly the same way, but the fluid density is now ρ plus delta ρ, the surface area is still A, and the fluid velocity is c minus delta v. Now, as A appears on both sides of the expression, we can cancel it. Next, let's expand out the product on the right-hand side. We then have ρc is equal to ρc minus ρ delta v plus delta ρc minus delta ρ delta v. Remember, each of these delta quantities is very small, and when you have the product of two small quantities, like in this last term, the result is extremely small. For example, 1,000th by 1,000th is a millionth. Thus, we can safely neglect this last term in comparison to the others. After cancelling the ρc terms that appear on both sides, we're left with 0 is equal to minus ρ delta v plus delta ρc, which we can rearrange to obtain delta v is equal to c times delta ρ on ρ. Let's label this expression 1. Next, let's apply conservation of horizontal or x momentum to our control volume. This tells us that, in the x direction, the total force on our control volume is equal to the integral of the momentum flux out of the control volume. The only forces acting on our control volume in the x direction are due to the pressures on the left and right sides. On the left side, this results in a force of P times A to the right, which is positive, and on the right side we have a force of P plus delta P times A to the left, which is negative. Now let's find the net momentum flux out of the control volume. There's no flow across the top and bottom of the control surface, so we only need to worry about the sides. Across the left side, the momentum entering the control volume is ρc, and the velocity of the flow is c. Now, because the flow is entering the control volume and we want to find the net flux out, this term is negative. As the flow is uniform across the face, integrating this momentum flux corresponds to simply multiplying by the area A. Similarly, on the right face, the integral of the momentum flux is ρ plus delta ρ times c minus delta v times c minus delta v times A. But as the momentum is exiting the control volume, this term is positive. Now let's do some simplification. A appears in every term, so we can cancel it. On the left-hand side, we have P minus P, which cancels, and from conservation of mass, this product of density and velocity is equal to ρc. So using this substitution, we obtain that minus delta P is equal to minus ρc squared plus ρc squared, which cancels, minus ρc delta V. We can rearrange this to get a second expression for delta V, which is equal to 1 on ρc times delta P. Equating expressions 1 and 2, we find that 1 on ρc delta P is equal to c delta ρ on ρ. Finally, we can rearrange this to show that c squared is equal to delta P on delta ρ.
Now, in the limit as delta P and delta ρ tend to 0, the wave becomes isentropic and c tends to the sound speed A. The ratio of differences we obtained, delta P on delta ρ, becomes the derivative of pressure with respect to density at constant entropy, which is equal to the sound speed squared. This tells us that sound speed is a direct measure of how difficult it is to compress a fluid. The higher the sound speed, the greater pressure increase required for a given increase in density. Unfortunately, this expression doesn't immediately allow you to compute the sound speed in the air you're currently breathing. To obtain a simple expression that can be readily evaluated, we need to take the derivative. This requires an equation of state for the fluid and what are known as the isentropic flow relations, which we'll cover in the next module. One thing we can immediately do is examine why the Mach number is such a good measure of compressibility.
When flow encounters an obstruction, the highest pressure occurs where the flow is brought to rest or stagnated. As we haven't got too deep into compressible flow theory yet, let's consider a near incompressible example. Low speed inviscid flow over a cylinder, as illustrated here. As the flow is nearly incompressible, Bernoulli's equation will approximately hold along a streamline from the undisturbed flow, state 1, to the stagnation point on the cylinder, state 2. Since V2 equals 0, Bernoulli's equation tells us that the pressure difference between states 1 and 2, delta P, is given by 1/2 ρ1 V1 squared. Rearranging this, we find that V1 squared is equal to 2 delta P on ρ1. Now, since the flow is inviscid, it's also isentropic. Therefore, the sound speed squared, which is equal to dp d rho at constant entropy, is approximately equal to delta P on delta rho, or delta P is approximately equal to a squared delta rho. Using this in our expression for V1 squared, we find that it's approximately equal to 2a squared delta rho on rho. Dividing this by a squared to convert it to a Mach number, we find that the Mach number squared is approximately equal to twice the relative change in flow density. So we see that the Mach number is an excellent measure of compressibility. It's giving us a direct indication of how much a flow might be compressed when it encounters an obstacle. In this low-speed example, we assume Bernoulli's equation holds approximately. But once we know a little bit more about compressible flow, we'll be able to solve this problem accurately for high Mach number flows as well.